If we think about impulse happening in collisions, we can think about Newton's third law, which says every action force has an equal and opposite reaction force. Since impulse is force times time, then in a collision between objects, the time is going to be the same because they're going to spend the same amount of time in contact with each other. Okay, so that impulse imparted to each mass is the same because the force is equal and opposite and the time would be the same. So we're going to compare the different types of collisions we've gone over. The first one on the left is perfectly inelastic collisions, and this is when they stick together and move as one mass after the collision. In this type, momentum is conserved, but kinetic energy is not because it's converted to other types of energy within the system. We're going to go over to the far right next and look at elastic collisions that we just talked about. These are when objects return to their original shapes and move separately after the collision, and they have really no impact on each other except a change in direction. In this case, momentum is conserved, and this is the only type of collision that kinetic energy is also conserved. Okay? Both of those two that we just talked about are actually pretty unrealistic for everyday life. Inelastic collisions in the middle is actually the most common. The objects are deformed even if it's slightly and then move separately. So they're bouncing off one another, but they do have some sort of deformation during the collision. In this type, momentum is conserved and kinetic energy is not. So in an elastic collision, the two objects collide and return to their original shapes with no change in total energy, and they essentially bounce apart or bounce off each other. So after the collision, they're moving separately. In this type of collision, a momentum is conserved, as they are in all types, but in this specific one, kinetic energy is also conserved. So one example of this that you may have seen in the past is Newton's cradle, which has the 5 balls hanging from strings, and if you pull one out, it will send one out on the other side when it bounces through. If you pull 2 balls out, we'll send 2 out on the other side as that bounces through, and so on. So let's look at a sample problem. A 16-kilogram canoe moving to the left at 12 meters per second makes an elastic head-on collision with a 4-kilogram raft moving to the right at 6 meters per second. After the collision, the raft moves to the left at 22.7 meters per second. Disregard any effects of the water, and we're going to find the velocity of the canoe after the collision. Okay, so they're just essentially bouncing off each other, so this is an elastic collision. So let's look at what we know. The 12 is the canoe's velocity, so that's the object 1, and we're going to make it negative because it's going to the left. The 6 is the raft's velocity, so that's object 2, and it's going to the right, so it will be positive. The canoe's final velocity is what we're going to look for. The 22.7 is the raft's final velocity, and it's going to the left, so we're making it negative. And then the mass of the canoe is 16, the mass of the raft was 4. So we're doing an elastic collision, so we're going to use the law of conservation of momentum as it's written, and we're going to plug in. So we have 16 times negative 12, that's the mass of the canoe and the initial velocity of the canoe, plus 4 times 6, that's the mass and initial velocity of the raft, equals 16 times final velocity for the canoe, plus 4 times negative 22.7, that's the mass and final velocity of the raft. So the first thing I want to do is multiply these numbers together. So I get negative 192 plus 24 equals 16 times velocity minus 90.8. Okay, I'm going to collect on the left side, so I add those together and I get negative 168 equals 16 times velocity minus 90.8. I'm going to add 90.8 to both sides. I get negative 77.2 equals 16 times velocity, and then I'm going to divide both sides by 16, and I get negative 4.8 meters per second. So that is the final velocity for the canoe. It's negative because the canoe is going to still be moving to the left after the collision.